Assalamu alaikum wa rahmatullahi wa barakatuh. We are still talking about the design of absorption column, and we are still talking about diameter determination. We are still using the same reference principles and modern application of mass transfer operations for James Pennede's a book that is available in your bookstore. So in the last session, we talked about the diameter. How can we estimate the diameter of a tray tower? In this session, we'll be talking about how we can calculate the pressure drop over every tray inside this tray tower. So the pressure drop across a sieve tray is basically caused by different reasons. So let's consider a tray. It's a sieve tray consisting of holes, obviously. And there's going to be liquid accumulated on top of it. The level of the liquid accumulation or the height of the liquid accumulation depends on the weir height on the tray. So the higher the weir, the more liquid is going to be accumulated on top of the tray. Now, when gas is passing from the bottom to the top, at the beginning, it will have to pass through the orifice of these holes, which is going to cause pressure drop, which is called HD, dry tray head loss. And the second reason for pressure drop is basically once the gas passes through the hole, it will have to push the liquid upward in order to be able to pass through it. So the weight of the liquid will be on top of the gas, and therefore in order for the gas to pass, it will have to carry the liquid upward in order to be able to flow through it. So this is basically HL, which is equivalent head of clear liquid on the tray. So obviously the higher the weir, the more liquid will be accumulated on top of the tray, and therefore the more the pressure drop we will have in terms of HL. So we'll have higher pressure drop. On the other hand, the higher the weir, the more liquid will be accumulated on top of the tray, and therefore more contact between the gas and liquid will take place, which means the mass transfer efficiency will be higher. So again, we have an optimization between pressure drop as well as compared to the height of the column. Now, once the gas overcome the weight of the liquid, the gas will have to pass through the liquid, which is basically will provide the third reason for pressure drop, which is head loss due to surface tension between the gas and the liquid. The liquid here obviously is the solvent. So three reasons for pressure drop. One is the head loss. The gas will have to pass through the hole, which is HD. Then second reason is HL, which is the gas will have to push the liquid on top of the tray in order to pass through it. And the third reason is basically the gas, there's going to be surface tension, friction between the gas and liquid, and therefore they will have a third reason for pressure drop. So the total pressure drop or the total head loss will be the summation of these head losses. And once we know the total head loss, we can convert it to Pascal per tray by delta pressure will be equal to rho GH, density of the liquid. G is 9.81 and H is the total H, and that's going to be pressure drop per tray. So let's see how we can calculate HD, HL, and H sigma. So the total head loss is the summation of the head losses due to the three reasons for pressure drop. So HD can be calculated using this correlation, which is basically mainly a function of V naught. V naught is the gas velocity based on the whole area. So V naught is the gas velocity based on AH. And we can calculate V naught by knowing that the volumetric flow rate of the gas will be equal to the gas velocity, the whole area, AH, multiplied by V naught. So V naught will be volumetric flow rate of the gas divided by the whole area. We have the density of the gas, we have density of the water as a reference number, and the density of the liquid. We have AH over AA, which we know already how we can determine this value. And we have C naught. C naught is a function of the hole size, D naught, and L, which is the thickness of the tray. So easily we can calculate HD. Next, we need to calculate HL, and HL is calculated using this correlation, where it has HW, which is the weir height, and LW is the weir length. We have QL, the volumetric flow rate of the liquid, and we have phi E, which is the effective relative froth density, which is basically the ratio between the height of the clear liquid without any bubbles, without any froth, divided by the froth height. If you don't know froth, just imagine a cappuccino where it has this froth layer on top of the liquid. So phi E is basically the froth density, which is calculated by capital KS, and capital KS is calculated in terms of VA, which is the superficial gas velocity based on tray active area, which is basically the volumetric flow rate of the gas divided by the active area, AA. And we have CL. CL can be calculated as a function of HW, which is the weir height, and again HW has to be in centimeter. The typical values for HW are between 2.5 and 7.5, which is something decided by you as an engineer. The higher the value of the weir height, the better the efficiency of mass transfer. However, at the same time, the higher the value of the weir height, the more the pressure drop and the more weight on top of the tray, which might cause weeping. Remember, we want to have zero weeping. The third reason for pressure drop is H sigma, which is calculated using this equation. Now remember, this is an equation, not like these correlations. So in these equations, all the units has to be consistent with each other. So sigma will be in Newton per meter, D naught will be in meter, G in meter square second, G in meter square second, and density is kilogram per meter cube, density of the liquid. So let's have an example of how we can utilize this correlation to calculate the pressure drop using the same problem defined during this basically chapter. It's the same ammonia absorber, and we have the weir height equal to 50 millimeter, which is 5 centimeters. So previously, from the previous examples we solved, we know the diameter of the column, we know rho G, we know rho L, we know the volumetric flow rate of the gas, we know AA, we know AH, we know the size of the hole, the thickness of the tray, and we calculated LW equal to 0.268 meter. So H total equal to the summation of the head losses. So let's start with HD. For HD, we need V naught, which is the velocity through the holes. Volumetric flow rate over AH is going to be equal to 20.8 meter per second. We need density of the water. In our case, in this example, the solvent itself is water. And we are assuming that the amount of ammonia in water is very small, that it will not change the value of density of the solvent. So density of water will be equal to the density of the solvent itself, 1000 kilogram per meter cube. We knew from the previous example AH over AA equal to 0.1. So now we can calculate C naught using 5 millimeter and 2 millimeter. C naught will be equal to 0.756. And then we can calculate HD by substituting everything, will be equal to 4.51 centimeter of water per tray. 4.51 centimeter of liquid, which is water, per tray. Then we need to calculate HL. For HL, we need to calculate VA. VA equal to the volumetric flow rate of the gas divided by the active area, which will be equal to 2.1 meter per second. Then we need the volumetric flow rate of the liquid, which can be calculated using the values we had from example 1 and example 2, which is equal to this value here. Remember, volumetric flow rate equal to the mass flow rate over the density of the liquid. Capital Ks can now be calculated easily, equal to this value. Then phi E will be equal to this value, 0.318. Then CL calculated using HW equal to 5 centimeter. Substituting everything in this correlation here, HW again 5 centimeter, HL will be 1.63 centimeter of liquid, which is water, per tray. Third reason for pressure drop is H sigma. Using this equation, remember this is an equation, not a correlation, so all parameters has to have consistent units. So sigma is 79 per centimeter, which is equal to 0.07 Newton per meter. We calculate H sigma by using D naught in meter. It's going to be equal to 0.0086 meter. Everything is in centimeter, so it's equal to 0.86 centimeter of liquid per tray. So now H total is the summation of these head losses, and they're going to be equal to 6.9 centimeter of liquid, which is water per tray. And we can convert it into Pascal per tray by multiplying rho, G, and H total. So it's going to be equal to 687 Pascal per tray, which is less than the maximum allowable pressure drop, which is 1000 Pascal, 1 kilopascal per tray, or in some references 1.2 kilopascal per tray. The last thing we need to check for is, do we have weeping or excessive entrainment? To know for weeping, we use Froude number through the orifice, through the hole, and which can be calculated using rho G, rho L, velocity of the gas through the holes. HL is the head loss, the amount of liquid on top of it. Remember, this is HL, head loss, not the weir height, HW. And we know how to calculate HL from previous slide. So Froude number has to be more than 0.5 to make sure that there is no weeping. So if it is more than 0.5, then there is no weeping. If it is less than 0.5, then we will be having a problem with weeping. I did calculate Froude number for the previous example, and Froude number was 1.79, which is more than 0.5, so there is no weeping. In terms of entrainment, entrainment is basically the ratio between how much liquid is carried out or carried away by the gas flow rate divided by how much gas is actually flowing up. So it is the liquid entrainment mass flow rate over the upward gas mass flow rate, which can be calculated using these correlations, which most of these parameters or all of these parameters are already basically defined either from the previous examples or can be calculated again using these correlations. And once we calculate E, we need to make sure that the value of E is not too high. And this is basically a judgment by the engineer whether this value is too high or not. Remember, the higher the value of entrainment, we will have low efficiency. Moreover, when we have really very high entrainment, then we will have flooding. The third problem is losing liquid in the gas stream. One, we are losing money, and two, that liquid in the gas stream might cause problems in the next processes like compressors or reactors or something like this. So we would like to maintain the value of entrainment as low as possible. But in general, if we have no weeping, no flooding, and pressure drop is within the range, then hopefully these values here will be as low as possible. So at home, I hope that you will give it a try, and for the same example you will calculate the value of entrainment in this design.